Similarly, liquid pressure acts in literal sites also. When a bottle having water is preside on the sides, we can see water coming out with a speed as in figure 3.3 C. This is C, 3.3 C. This is because liquid exerts lateral pressure on the walls, the container. Activity 2. Take a transparent plastic pipe also. Also take a balloon and tie it tightly over one end of the plastic pipe. Pour some water in the pipe from the top. What happens? The balloon tied at the bottom stretches and bulges out. It shows that the water poured in the pipe exerts a pressure on the bottom of its container. Factors determining liquid pressure in liquids. Pressure exerted by a liquid at a point is determined by depth h, density of liquid p, acceleration of due to gravity g. Density of the liquid is p, depth is h, and acceleration due to gravity is g. Activity 3. Take a large plastic can, punch holes with a nail in a vertical line on the side of the can as shown in figure. Then fill the can with water. The water may just dribble out from the top hole, but with increased speed at the bottom holes as depth causes the water due to squirt out with more pressure. From this activity, we can infer that pressure varies as depth increases, but it is aimed at a particular depth independent of the direction. Activity 4. Take two liquids of different densities, say water and oil, to a same level in two plastic containers. Make holes in the two containers at the same level. What do you see? It can be seen that water is squirting out with more pressure than oil. This indicates that pressure depends on density of the liquid. Pressure due to a liquid column. A tall breaker is filled with liquid so that it forms a liquid column. The area of cross section at the bottom is A. The density of the liquid is P. The density of the liquid is P. The height of the liquid column is H. In other words, the depth of the water from the top level surface is H. As shown in figure 3.4. Pressure due to a liquid column. We know that pressure just at the bottom of the column F equals weight of the liquid. Therefore, F equals mg, milligram. We can get the mass of the liquid by multiplying the volume of the liquid and its density. Mass M equals P V. volume of the liquid column V equals area of cross section A into height H equals AH. Substituting 3 in 2. Mass M equals P AH. Substituting 4 in 1. Force equals mg equals P A H G. Pressure P equals thrust F by area A equals mg by A equals P AHG by A equals PHG. Pressure due to a liquid column P equals HPG. This expression shows that pressure in a liquid column is determined by depth, density of the liquid and the acceleration due to gravity. Interestingly, the final expression of the pressure does not have the term area A in it. Thus, pressure in liquid depends on depth only. Problem 2. Calculate the pressure extended by a column of the water of height 0.85 m. Density of water P W equals 1000 kg m power by minus 3 and kerosene of same height, density of kerosene P K equals 800 kg m power by minus 3. Solution. Pressure due to water equals HPWG equals 0.85 m meter into 100 kilogram meter power by minus 3 into 1000 kg. This is 1000 kg, sorry, into 10 ms power by minus 2 equals 88,500 Pa. Pressure due to kerosene equals HP kg equals 0.85 m into 800 kg m power by minus 3 into 10 ms power by minus 2 equals 6,800 Pa. 3.3 Atmospheric pressure. Earth is surrounded by a layer of air up to certain height, nearly 300 km, and this layer of the air around the earth is called atmosphere of the earth. Since air occupies space and has weight, it also exerts pressure. This pressure is called atmospheric pressure. The atmospheric pressure we normally refer is the air pressure at sea level. Figure 3.5 shows that air gets thinner with increasing altitude. Hence, the atmospheric pressure decreases as we go up in mountains. On the other hand, air gets heavier as we go down below sea level like mines. Atmospheric pressure acts like a column. This is the figure 3.5. Measurement of atmospheric pressure. The instrument used to measure atmospheric pressure is called barometer. A mercury barometer, first designed by an Italian physicist Torricelli, consists of a long glass tube closed at one end, open at the another, filled with mercury and turned upside down into a container of mercury. This is done by closing the open end of the mercury filled tube with the thumb and then opening it after immersing it into a trough of mercury. Figure 3.6. This is the mercury barometer. This is the barometer. Mercury barometer. This is. Thank you for all my friends.